Today, we are diving into some really fascinating new tech that could totally reshape how we get fresh water. It's all based on a recent paper in Nature Communications, and trust me, it's a wild ride.
I mean, just think about that question for a second. It sounds like something straight out of science fiction, right? But that is the actual, literal idea we're exploring today. We're talking about a material that can reconfigure itself on demand to tackle one of the biggest challenges we face. So before we get to the cool stuff, let's just quickly set the stage. Because this isn't some abstract problem. It's a global reality, and the stakes could not be higher. Yeah, you heard that right. Over 2/3 of the world's population, we're talking more than 4 billion people, has to deal with water scarcity in some way. And this isn't a problem for the future. It's happening right now, which makes the hunt for a breakthrough more urgent than ever. Okay, so one of the most promising ideas out there is something called interfacial solar steam generation, or ISSG. The concept is actually pretty simple and, kind of elegant. You get a material that floats, it soaks up sunlight, and it heats up only the very top layer of the water. That creates steam, leaving all the salt and gunk behind. It's super efficient because you're not wasting all that energy heating up a giant tank of water. But, and there's always a but, here's the catch. While the idea is fantastic, the traditional ISSG systems have kind of hit a wall. See, they're static, they just sit there. And that creates some major problems. There are two big issues that really hold these static systems back. First, the obvious one, salt. As the water evaporates, it leaves the salt behind, and pretty soon the whole surface gets clogged up. But the second problem, the one you might not think about, is the steam itself. It just kind of hangs around, creating this humid bubble that traps heat and slows the whole process way down. And that turns out to be an even bigger deal. And you can really see that salt problem perfectly right here. On the right, that's your traditional flat evaporator. After just 12 hours, look at it. It's completely caked in salt, totally blocking the sunlight. Now, the cone design on the left is better, for sure, but you can still see that salt is a huge issue. But again, that bigger, sneakier problem is the trapped water vapor. And honestly, the wet blanket analogy is perfect. It's like trying to dry off in a super steamy bathroom, right? The air is already full of water, so nothing evaporates. That humid bubble just sits on the surface and grinds everything to a halt. Scientists call this water vapor diffusion, or the lack of it, and it was the key problem that somebody needed to solve. So, to get around these problems, researchers needed a totally new kind of material. Something smart, something responsive, something dynamic. So let's meet the hero of our story. At the very heart of this solution are these incredible little nanoparticles. And how they're made is really clever. They start with a tiny magnetic core of iron oxide. Then they basically use static cling to wrap that core in sheets of graphene oxide, which they then process into this super absorbent form of graphene. And this whole core shell design gives each tiny particle a set of superpowers. That iron core makes them magnetic, which is absolutely crucial for controlling them. The graphene shell is an amazing solar collector. It soaks up over 98% of sunlight to generate heat. And that shell also stops the particles from clumping together, which lets them form these complex, porous structures that can be reshaped whenever you want. Okay, now for the really cool part. Having a great material is one thing, but the real genius here is how they use it. This is where static design gets left completely in the dust. So check this out. When you apply a magnetic field from underneath the water, these nanoparticles spontaneously build themselves into this perfect array of tiny little cones. And because they're magnetic, if you start moving the magnet, the cones move with it. They can tilt, they can rotate, they can literally dance. And this introduces motion on both a big macroscopic scale and a tiny microscopic scale. And here's the most important point. This dynamic motion, this dancing, isn't just for show. It is designed to directly attack those two big bottlenecks we talked about earlier, that trapped water vapor and that crusty salt buildup. Okay, first let's talk about the big macroscopic motion. As the cones are rotating and tilting around, they're acting like a whole army of tiny fans. They're physically pushing that wet blanket of humid air away, which lets drier air come in and speed things up. And the proof is right here in this thermal image. The one on the right is the dynamic, moving cone. See how its surface is so much cooler? All that blue? That's not because it's generating less heat. It's because it's evaporating water so incredibly fast that it's actively cooling itself down. That's proof it's working. But here's the part that is even more brilliant, the microscopic motion. While the whole cone is moving, the individual nanoparticles inside the cone are also constantly shuffling around and rearranging themselves. And this constant internal churning creates this tiny circulation that actively pulls fresh water up from below and pushes the super salty water away from the surface. It prevents that salt crust from ever even forming in the first place. And look, this isn't just a theory, they actually proved it. The researchers put these tracer particles, you can see them there in cyan, only at the very bottom of a cone. That's image II. Then, they set the whole system into dynamic motion. And when they looked again in image IV, those tracer particles were spread evenly through the entire cone. That's the smoking gun that this rapid internal mixing is really happening. Okay, so we've got a dynamic system that brilliantly solves the two main headaches of salt and trapped steam. But what does that actually mean for performance? Well, the results are where this story gets truly unbelievable. Just by adding this dynamic motion, just by making the cones dance, the researchers immediately got a 23% jump in the evaporation rate compared to the exact same cones just sitting still. I mean, that alone is a huge improvement. But they were just getting started. They then used the reconfigurable nature of these nanoparticles to design the ultimate evaporator. They called it a hierarchical assembly. To me, it looks like a tiny, weird alien forest. This whole structure is engineered to get the most surface area possible while also creating these big channels for all that water vapor to escape. And this chart says it all. A standard flat system on the far left gets you about 1.6 kilograms of fresh water per hour. The static cones are a little better, but the dynamic, tree-like assembly, 5.88 kilograms. That's more than a 3.5 times improvement over the standard method. It's a truly record-breaking level of performance. So you see, this is way more than just a better way to desalinate water. What we're looking at here is a fundamental shift in how we can design materials and systems to interact with the world around them. The researchers themselves put it perfectly. The key here is the move away from static systems to what they call dynamically adjustable ones. So instead of building rigid things that just break down over time, we can create systems that actively maintain their own efficiency through motion and self-reconfiguration. And that really leaves us with a powerful final thought. We just saw how teaching a material to move, to dance, led to a record-shattering solution for water purification. So it really makes you wonder, what's next? What other massive problems in energy or medicine or cleaning up the environment are just sitting there, waiting for a smart, dynamic material to come along and literally shake things up?